step in an algebra problem. So these are deductive arguments, and we're going to talk about something we call a two-column proof when we use these algebraic proofs. So these are the reasons that we use in our algebra proofs. Now we're going to go through each of these, and a lot of these you've already seen before, if not all of them. Okay, but these are the properties or the reasons we can use when we solve an algebra problem. So let's go through each of these individually. First of all, we had one called the reflexive property. The reflexive property just says something's equal to itself, right? We call this reflexive property. Okay, so if I said prove that 3 is equal to 3, you would say 3 is equal to 3 by the reflexive property. Something's equal to itself. Okay, 5 is equal to 5. Negative 1 is equal to negative 1. Just something's equal to itself, we call that reflexive. Okay, so that's the property we use. If you're ever asked to prove something's equal to itself, it's by the reflexive property. Okay. Then we had something called the symmetric property. Okay. So the symmetric property just says, right, symmetry means it's the same on both sides. The symmetric property just says you can flip around what's on each side of the equal sign. So if I give you this, if this was your given, and I said prove that, if I give you 1 plus 2 equals 3, and I said prove 3 equals 1 plus 2, you would say that's true by the symmetric property. Okay. Because all the symmetric property says is what you can flip around what's on each side of the equal sign. It doesn't matter. Okay? And you can change it. So if I ever asked you to prove something's different on the other side of the equal sign, you would just say that's true by the symmetric property. Okay? Then we had what I call the KU football property, transitive. Right? Remember we talked about this a while ago, that KU should have been national champions in football, right? The transitive property says if A is equal to B and B is equal to C, then A is equal to C. Or in our case that we looked at last time, if A is better than B and B is better than C, then A must be better than C. Right? That's the transitive property. So for example, if I gave you, if you're given 4 plus 3 equals 7, okay, and 7 equals 5 plus 2, prove that 4 plus 3 equals 5 plus 2, right? This would be by the transitive property, okay? If 4 plus 3 equals 7 and 7 equals 5 plus 2, then 4 plus 3 must equal 5 plus 2. If A equals B and B equals C, then A must equal C. It's a transitive property. If the first and second thing are equal and the second or third thing are equal, then the first and the third must be equal. Any questions with those three first? So those are three properties that we can use when we're using these algebraic proofs. Okay. The next one, these ones we've been using for a long time. If I give you x minus 3 equals 10, prove that x equals 13. Okay. Well, what are you going to do to both sides to solve for x here? You're going to add 3, right? You're going to add 3. You're going to undo the subtraction by 3. So you would add 3 to both sides of the equal sign. But whenever we do algebraic proofs, we always have to give a reason for everything we do. So that's just called the addition property. Okay. The addition property says you can add something to both sides of the equal sign as long as you do it to both sides. Whatever you add to one side, you have to do to the other. And you would get x equals 13. So I would say x equals 13 by the addition property here. I added 3 to both sides of the equal sign. And it's the exact same thing for, in this case, if I said prove x equals 7, you would subtract 3 from both sides. Okay? And that would be by the subtraction property. The subtraction property says you can add or subtract the same thing from both sides of the equal sign. We've been doing that stuff for a long time. Right? Then we had, if I gave you 3x equals 27, and I want you to prove that x equals 9, what are you going to do to both sides here to solve for x? Yeah, you're just going to divide, right? So you would divide by 3, you divide by 3. That's called the division property. Okay? Division property says you can divide by the same thing on both sides of the equal sign and it's still true. Okay? And then, of course, we had the same thing for multiplication. If you had something like this, prove that x equals 30, you would get rid of the division by 2. You would multiply both sides by 2 to prove x equals 30. That would be the multiplication property. Okay. So you've been using the addition, subtraction, multiplication, and division properties for a long time. Now we just have a name for them when we use them, okay, in an algebraic proof. So those four, and then the last two we call substitution and distributive property. You've used distributive property a long time as well. If I said given, if I said you're given this, prove this, what are you going to do here? You're going to distribute the 2, right? You're going to take 2 times x plus 2 times 1, and that would be by distributive property. Okay. So we're still just working the same old algebra that we've been working a long time. Now just every time we do it, we have to give a reason for what we do. Distributive property is one of those reasons. Okay. And then the last one is substitution. So if I said given sorry, let me change this. So if I gave you this one, if I give you x plus y equals 15 and x equals 5, I want you to prove y equals 10. Well, what's the first thing you're going to do to solve this algebra problem? You're going to plug in 5 for x, right? So you're going to get 5 plus y equals 15 by substitution, right? You have to give a reason for everything by substitution. Then what are you going to do to both sides to solve for y? Subtract 5, subtract 5. Y equals 10 by, what did you do? Subtraction property. Right? And there you just proved y equals 10. Okay. So I did substitution property, then I did subtraction property to prove that y equals 10. Those are the reasons you're going to give to solve these algebraic proofs. Okay, one of those. Yeah. When we're solving, let's go through one example here. Okay. Remember, in every proof, I'm going to erase this. In every proof, there's always a given and there's always what you're trying to prove. Now, you can do it just like we did it, but one easy way people start to do it now is we put it in 2 columns. Is we make what we call a 2-column proof. And on this side, we put what we call our statements, and on this side, we put our reasons. Okay? So these will be our justifications, our reason, and this will be our work. A lot of people do it this way. You don't have to do it this way, but this is a good way to do it. And every time that you do one of these, you always start with what's given to you. So I'm going to start with x plus y equals 60 and x equals 5, and my reason for that is that's what's given to me. In every proof, they have to give you something to start with, and you always list that first. Okay? So if I want to prove y equals 55, what's going to be my first step in this proof here? Yeah, just plug in x equals 5, right? What's my reason that I did that? How was I able to do that? Substitution, right? And then I want to prove y equals 55, so I need to get rid of that positive 5 on both sides. Subtract 5. And I was able to do that by the subtraction property. Okay? That's a perfectly good algebraic proof. You just solved an algebra problem giving every step along the way. Okay? We use substitution and we use subtraction property there. And you did it in a 2-column proof. You don't have to do it in a 2-column proof like this. You could just write it out in words, right, if you want. But you could also just put your reasons over here and your statements over here. Okay. Now we need to have a reason for when we combine like terms, because you can't write combine like terms as a reason. That's not an algebraic reason. That's just something we do. Okay? What we write when we combine like terms is we call that substitution. The reason is, you would combine these two are like terms, right? Negative 6a minus 4a. That would be negative 10a. Okay? And then you could also combine these like terms. 10 minus 28 would be negative 18. Right? Our justification for this, we call this substitution. Substitution is another word for combining like terms. The reason is because we substituted in negative 10a for this piece. And we substituted in negative 18 for 10 minus 28. So you never write combined like terms over here. You would just call it substitution. Okay, because you're substituting in something that's a more simplified version. So combining like terms is not a valid reason or not a valid property. You would call that substitution. And then you would continue this. Now, if you're still finishing up, that's fine. Just check it as we go. Okay, but I'm going to go over two perfectly good ways to do it, because there's one way that I'm okay with you doing it and one way that the book mainly does it. And I'm going to go over the differences between the two. So let's go over the way you probably did it first. So we're trying to prove D equals 3. That's what our end goal is. Okay, so what's going to be our first step here in solving for D? Yeah, we're going to get rid of that division by 4, right? So we're going to multiply by 4, multiply by 4. Those cancel. We're left with 7D plus 3 on that side. We're left with 24 on that side. And what was our justification? What was our reason for doing it? Multiplication property. Okay. Okay. That's why we were able to do that. Remember, we can't subtract 3 first because the subtract 3 is kind of trapped by this division right here. Right? We have to get rid of the division first. What's going to be our next step in solving for D? Right, move the 3 over. Okay, that would give us 7D equals 21. We were able to do that by the subtraction property. Okay. And then finally we would divide by 7, divide by 7. We would get D equals 3 by the division property. Okay. Now, what if I was to say, instead of proving D equals 3, I want you to prove 3 equals D? What would you now do at the end of this proof? You would write 3 equals D by what property? What property lets you switch what's on each side of that equal sign? Yeah, so then I would say symmetric. Okay. Every time you do something in a proof, you have to give a reason. So if I told you prove 3 equals D, at the end you would just switch them and say the symmetric property. Okay. But I didn't, so you didn't have to put that there. Okay. Now, that's a perfectly good way to do that. You do that, you clearly know what's going on, and you got everything there. Now, the way the book does it, though, a lot of the times, is they will write each step, and every time they simplify, they write that substitution. So what I mean by that, and you don't have to rewrite this, but they would do this. They would write that's multiplication property. Then they would write this. And they would write that's substitution property. Then they would write this is subtraction property. Then they would write this is substitution property. So what they're doing, okay, the difference between what they did and what we did the multiplication and subtraction ahead and simplified. They wrote every time you simplified, they substituted in 24 for 6 times 4. They substituted in 70 plus 3 for 4 times 70 plus 3 over 4. They substituted in 7D for that. So every time they did something, they simplified, which we call substitution. You don't have to do it this way. The only reason I want you to know that is because I think on one of the homeworks there's a fill in the blank proof. Like they do it, you just have to fill in the reason. Whenever you simplify or whenever you combine like terms, we call it substitution. We also call substitution when you plug something in, but whenever you just simplify it, we call it substitution. The way we did it the first time, I'm perfectly okay with you doing it that way. You don't have to write substitution between every step. Does that make sense? Okay.